Okay, so let's move on. So we talked about general spectroscopy, general units to use, how you convert between them, and now we're going to move on to the first spectroscopy. We're going to talk about UV visible spectroscopy. So here you have, in most spectroscopies, you have to have some light source. So here we have our little animated light source. And let's see if we move on this slide. I think we have yeah. So you're going to get some UV radiation from that. But usually you're going to get more than one wavelength. And for spectroscopy purposes, we want to just see, for this purpose, we want to see just one wavelength. So you have a monochromator here. And the function of the monochromator is to select a single wavelength from the wide range provided by the light source. So we're not going to get into instrumentation here. We want to get the main principles, but this monochromator selects a single wavelength. And then you have this incident, one wavelength, and you have what we call incident light. So this is the light that's going in to the sample. Here's our cell here that contains our sample. So you have an incident photon, and what we give this, we call this I, capital I, and subscript 0. So that's our I0. And then it goes through the cell, and what we're trying to show here is, you can see it's thicker here than it is here. So the idea is that some of it is absorbed and less of it comes out, and then you have some detector that can detect that light there. So that's the basic principle of any kind of a spectrometer, if you like. You have a source, some kind of thing that will select wavelengths, goes through a cell, and then you have the detector. So you have I0 going through, and the light that comes out, or light that's not absorbed by the sample, is I. So for this type of spectroscopy, again, just small points on technical. You have a cell that's called, sometimes called a cuvette, glass to plastic, but you maybe have quartz for UV light. So that's just the technical side. So what we're interested in is what's going on when that incident radiation, it goes in I0, and then some of it's absorbed, and it comes out as having an I value. So there's three factors that will govern the amount of of absorbance. So we're going to put these very qualitatively first. The thicker the sample, the more absorption. That basically means how big amount is in the cell, if you like. The thicker the sample. It's a bit unscientific there. And also the concentration of the sample. So you have a different concentration of your solution in that cuvette. And then there's this inherent factor that some molecules are better at absorbing at a particular wavelength than other ones. All right. So the thickness of the sample, the concentration of the sample, and then an inherent property of the actual molecule, how much energy it can absorb. So to get this in a more quantitative way, this is a bit qualitative in the last slide. This was developed by people called Beer and Lambert. So it's called the Beer-Lambert law, and we're also, I'll emphasize this a few times, we're referring here to just at a single wavelength. So it's the Beer-Lambert law, and it also always refers to a single wavelength. So the absorbance of the sample depends on the concentration, I've already mentioned this, of the absorbing species. Now we're getting a bit more quantitative, and we measure concentration in moles per liter. That's moles liter to the -1, or sometimes you have moles per decimeter cubed. Moles decimeter to the -3. Same thing. So we're going to, at this side, we're sticking at moles per liter. Then you have the length of the light path. We crudely mentioned that because of the thickness of the thing before, but it's the length of the light path, L, through the cell. And it's usually quoted in centimeters. It's in SI units, we should be talking about meters, but historically, this kind of spectroscopy, people refer to centimeters. Again, because I think it's the easier unit, usually the cells are just a few centimeters, so it's easier to talk about centimeters. But the length of the path cell is usually given in centimeters. And then you have this, we said, this inherent ability of the molecule to absorb the light, and that's known as the molar absorption coefficient. And it's given this Greek letter epsilon here. And the units of that are liters, or decimeters cubed, moles minus 1, centimeters minus 1. So the absorbance, we define the absorbance of a sample with these three quantities. We define this the molar absorption coefficient multiplied by the concentration multiplied by L. And strictly, you don't need to worry about this too much. We're talking about one wavelength, so we're talking about the absorbance at a given wavelength is equal to epsilon at that given wavelength, because that will change depending on the wavelength. So anyway, so remember, A is equal to epsilon CL. And then you have just the molar absorption coefficient, which this is an inherent property, and some molecules are better at others at absorbing at particular wavelengths, inherent property, and it's also known as the molar absorptivity and the extinction coefficient. So there's a few names for it. So we'll call it the molar absorption coefficient. Right, so let's move on to this, talk another bit about this. So we have our incident light, and here's our cuvette. So we have I0 coming in, we have I coming out, and we need to know a relationship between the light coming out I and I0. We've already defined the something called the absorbance as epsilon CL. And the relationship between these two is given by this equation here. Now you can derive this. This is called the first order. This is actually first order rate law. You can derive that. We're not going to do that. You just have to accept from me that that's what is given. So I is equal to I0 10 to the power minus epsilon, which is also our molar absorption coefficient, L the length of the packed the cell, and C the concentration. So that's another definition, if you like. We've already had the absorbance. We've already had the absorbance, which is equal to epsilon CL. So now we have that the absorption also is equal to this. Now, if you know a bit of, let's see if we can do the mathematics, how we can get to that. So we have I is equal to I0 10 to the minus epsilon CL. So if we go I over I0 is equal to 10 to the minus epsilon CL. So now if we go I0, if you know your lower logs, I0 over I is equal to 10 to the epsilon CL. So just if you invert one side and you change the sign here, so you know that the log to the base 10 of I0 over I is equal to epsilon CL. So I don't know how good your mathematics is, but that's just working from this equation here. So you know that the log of there's 10 of I0 over I is equal to epsilon CL, and that's equal to A. So that's where you get that relationship between the absorbance and the transmitted. So you have the incident light, transmitted light. Right, let's move on. So this is just a carry on from the that the transmittance is equal to I over I0, the light that comes out, the intensity of the light that comes out, divided by the intensity of the light that goes in. And therefore, going back to the last slide, you can work out that it's A is equal to negative log 10 of the transmittance. Just to remind you again, I think we worked it out here. I over I0, that's defined as the transmittance. So again, if you take the log of that, you're going to get minus epsilon CL, which is minus A. Okay? So you can either remember these, or you can try to do the mathematics, which is usually the best way. You remember them for a long run.